Now we're going to go in and we're going to look at the properties of exponents. Um, Properties of exponents are really important and very handy inside of, say, things like induction and recursion. They're also very handy for working with, time complexity and space complexity and things of that nature, because it just comes up that we're going to end up having exponential functions. We're going to be talking about like exponential growth. We'll also be talking about what happens when you have like summations of exponentials. And so, hence, these properties of exponents can be really very valuable for working with those sorts of things. So this should be a bit of a review. If you want to actually look at stuff get a clearer view of why these properties of exponents work. There are a lot of really great videos for that. I think I have one actually for my calculus classes. And so you can go take a look at those. This is really just going to go over the rules. It's going to go over how to use those rules from an algebraic perspective. And then we'll do a little bit of mixed practice where we kind of work with those rules. The first property that we're going to be working with is something called the addition property. So the addition property, first we want to recognize a couple of things, a little bit of vocabulary. This is B is called the base of the exponent, and the x's and y's here, they're called the exponents. Sometimes also called the powers. Okay? So when I say base, what I'm talking about is I'm talking about the value at the bottom, and then the exponents are the things that are the powers. Okay? The addition property here is going to say that if I've got two numbers that have the same base, okay, whatever that base is, doesn't really matter what it is as long as it's the same, and I raise those to a power, what I can do if I'm multiplying them is I can actually then go in and add the exponents, right? It's kind of easier to look at and see from some examples than to kind of explain. So let's say, for example, I have 6 to the k, okay, times 6 squared. What I can do is notice, one, the base is the same here, so consequently I can go and add the exponents, 6 to the k plus 2. Let's take, for example, I've got 3 to the 4th times 3 to the 9th, right? And I may be like, oh, I don't want to go calculate 3 to the 4th. I don't want to calculate 3 to the 9th. Instead, I notice that they have the same base, so I can make this 3 to the 4th plus 9, which is 3 to the 13th. And there we are. Perfect. Couple things to notice too, and I have a couple of ones that we should remember. 3 to the 0th power is equal to 1. All right, and so consequently, if we ever get that, we're going to see that that's the case. So for example, if I take 3 to the 5th times 3 to the negative 5th, this is actually 3 to the 5th minus 5, and that's 3 to the 0, which equals 1. I should change this, not just 3 to the 0, b to the 0. Any base to the 0th power is going to equal 1, and that's always true. Now we can also go through and we can expand this out, because sometimes that's actually really handy to do. Let's say, for example, I have 5 to the 15th. I can actually notice that this is 5 to the 10 plus 5, which equals 5 to the 10th times 5 to the 5th. And that is called an expansion. Okay, what we've done is we've gone from addition inside in the exponent to a multiplication with the exponent separated. And that is the addition property. Let's say we see an example like this. This is called our multiplication property. And so the multiplication property says, okay, I've got b, that's my base, and I'm going to take it to the next power, and then I'm going to take that whole thing to another power. And if I do that, then what I can do is I can actually have b, and I'll just multiply x times y. I'll multiply the powers. You're sometimes going to see this called power to a power. That's one of the ways it's actually stated as well. But we're just going to call it our multiplication property. Doesn't really matter what you call it. It really matters if you understand what it is that you're doing. So let's take, for example, I've got 6 cubed, and I'll take that to the 5th power. And notice we've got this power to a power. We end up with, that's 6 to the 15th power. And there we go, because 3 times 5 is 15. Let's say we have k to the 2k to the k plus 1. Now what we want to do is we just want to remember, it doesn't matter the fact that these are actually variables. Power rules work all the time the same way. So this is now going to be k to the 2k times k plus 1. If we wanted, we could actually go through and distribute that using a little algebra. We get k to the 2k squared plus 2k. Okay, so sometimes you see things that look like that because we're working kind of abstractly. You might see that working with time complexity or algorithms or any kind of recursion. All right, let's say, for example, now we have 6 to the 18th power. We could actually break that up, or rather, not 6 to the 18th power, pardon me, 6 to the 16th power. We might notice that 16 is actually 4 times 4, so we could write this as 6 to the 4th power, okay? And that would be an expansion. We could go in and we could actually expand out, right? In fact, let me write this. This is 6 to the 4 times 4, and that equals 6 to the 4th power, right? Notice we went from multiplying to power to a power. So we actually went the reverse way. Let's say, for example, we do something along these lines. One of the things that you'll see sometimes is you'll see like 6 to the 5th or 6 to the nth power times 36. We're like, well, what do you do with that? Well, you'll notice that this is 6 to the n, and then this is times 6 squared. And so consequently, it's really handy to know your powers, at least up to the squared powers, or to have an instinct about whether or not a value is, in fact, the power of another discrete number or another integer, right? Because in this case, what we can do is we can use our power to a power, and we can get 6 to the n plus 2. We note that 36 is 6 squared, okay? So that gives me then 6 to the n times 6 squared. We've got the same base, okay? And then we add them. And there you are. Well, that actually was more of the addition property, wasn't it? Oh, there you go. Let's do one more of this power to a power. Let's say, for example, I have 6 to the 2k, okay? Or actually, this is what we'll see more often. Let's say I have 36 to the kth power. I can note that this is actually 6 squared to the kth power, and now I use power to a power, and that gives me 6 to the 2k. Okay, so these are like some pretty common things that you'll see with with working with exponents. This is addition property, not power to a power, but this one here is in fact power to a power, and you'll see that, and that actually is pretty common. So here we have our subtraction property. And our subtraction property says I've got two values that are the same base. They've got exponents. They may be different. They may be the same. And so what I can do if we have a quotient of those two is I can actually then make a single exponent by subtracting my exponents. So for example, if I had 2 cubed over 2 to the 1, or excuse me, 2 squared, that would end up being 2 to the 3 minus 2. Okay? And so that's 2 to the 1, and that just ends up equaling 2. You can actually go in and use your calculator to see that that's the case, right? So what we did, we had a quotient of two exponents, or excuse me, two exponential functions, and we just went in and we subtracted out their exponents since they had the same base, and there it is. That's the subtraction property. Let's take, for example, we'll do 5 to the k over 5. Now 5 is just 5 to the 1, so this is going to be 5 to the k minus 1. Let's say that what we have is we have 6 to the n over 216. It turns out that 216 is actually 6 cubed. So this ends up being 6 to the n over 6 cubed. So we get 6 to the n minus 3. We can also expand out if we needed to. So let's say, for example, that I have now, instead of I have my exponents over each other, let's say I have 6 to the x minus 6y. And what this will then equal is this will be 6 to the x over 6 to the 6y. So what we can do is if we have a subtraction of two values in the exponent, we can actually, in fact, turn those into a quotient as long as we keep the base the same. So what that is, that's just our subtraction property. That's how that works. All right, so now the last property we're going to look at, we're going to call it the same exponent property. In all of our previous examples, we had seen something where the base was in fact the same. And so that allowed us to expand or contract our exponential statement. In this case, that's not going to be the case. What instead we have is we have b, c to the x. So we've got actually two different bases, but this is then going to be b to the x, c to the x. Okay? The thing is we notice now that the exponent is in fact the same. So the exponent is the same, but the bases are different. And so what that means is that basically means we can kind of distribute the exponent, right? So we'll take an example. Let's say, for example, I've got 3 times 2 to the 6th power, okay?
Well, now I can just rewrite this as 3 to the 6th times 2 to the 6th. And there we go. Let's say, again, let's say I've got 72 to the 6th power. Or 72 squared. All right. And I'm like, okay, well, what is that? Let's say it's 36 times 2 squared. And we can actually, if we wanted to, we could rewrite 36 as 6 squared. So we'll make this into 6 squared times 2 squared. And then we'll use our same exponent property to give me 6 squared squared times 2 squared, which equals 6 to the, well, notice that's our multiplication property, or power to a power. So 6 to the 4th times 2 squared. So sometimes we do some creative things or crafty things. If, say, for example, we want to get, let's instead now, let's take a look and see something a little bit more common. Let's say I have 5 to the x and 4 to the x. Well, notice that we actually have the same exponent. And so what we can do then is we can bring these in. That's now 5 times 4 to the x power, right? So we've gone from this side where we have two separate bases, different bases, but the same exponent. And we then go in and we'll bring them both into the parentheses and multiply them. So this now equals 20 to the x power. Okay? And that's how the same exponent property works. So we've got these properties of exponents. There are a couple of things that you want to remember because they're going to make your life a bit easier as you're working through stuff like this. Let's say, for example, 1, we want to remember that 6 to the 0 equals 1, or b to the 0 equals 1. Not just 6 to the 0, but b to the 0. So anything to the 0th power is going to end up equaling 1. B, like just a value b, is also equal b to the first power. And so sometimes that actually could be really handy. That could be a really powerful thing to get. So like, for example, if I had 5 to the k over 5, if I remember that this is actually 5 to the k over 5 to the 1, I can then subtract my exponents and I get 5 to the k minus 1. Okay, and that ends up becoming a really handy thing to know. It comes in kind of handy as we're kind of solving things or doing work just in general in mathematics and discrete math in particular. Okay, all right. And so those are just some things that we kind of want to remember as we're going forward. You've got your 4 properties. Here's a couple of things to kind of remember. And good luck working on these as you work through your homework.